Okay, I'll get started. Just a reminder that if you've any questions about Test 2 or any questions about Test 2 grading, feel free to come and see me or see your recitation instructor. I'll have the solutions to Test 2 posted today because now all the makeups are over. Any questions on all that? Okay, then I'll begin with the class today. The class today, we're going to continue working on the properties, nature, characteristics of light. We're going to be focusing on the property of reflection of light today. We're going to be focusing on reflection of light from mirrors, from flat, what we call planar mirrors, to curved, what we call concave and convex mirrors. That's the world that we're going to explore today. Specifically, in today's class, I want to go through these three items. I want to make some remarks about the formation of images of objects in optics. So what is an image? What is an object in this world of optics? So I'll say a few general remarks of that. That's going to apply to today's class. It's going to apply to next class. So it's just some basics for today's class and next class. Then we're going to work on the images that are formed by reflection off a plane mirror. That's a flat mirror. And we'll look at some illustrations in the class today of that. Then we're going to work on the images formed by curved mirrors. That's what I call convex and concave mirrors. And we'll also look at some examples of that in today's class. When we look at the images formed by planar mirrors and curved mirrors, we're going to examine the images formed in two different ways. We're going to examine their formation through equations, formulas for the image formation and the properties of the image. We're going to investigate the image by ray tracing, by drawing the images and investigating the properties of the image. So we're going to do it those two ways. I'll make a remark that the reflection, the images formed by mirrors, the understanding of the images formed by mirrors, that's today's class, and the images formed by lenses, the understanding of images formed by lenses, were the birth of modern biology and modern astronomy, because they allowed the development of astronomical and biology instruments. They allowed the development of the microscope, for example, and the telescope, for example, that were the basis of modern biology and modern astronomy. So the work that we do in today's class with reflection of mirrors and the work we'll do in the next class with images formed by lenses were the basis for really igniting the fields of astronomy and biology. Okay. So this is a general remark. This applies to this class, it applies to the next class, and later classes too. What is an image? What is an image? An image is a copy or a likeness or a representation of some object. So a tree might be an object, and then we could make an image of the tree. That would be a visual copy of a visual likeness, a visual representation of the tree. You could be the object, and then an image of you that would be a copy or a representation or a likeness of you. On this slide are two examples of images that are formed of objects. One on the left here, this is an image formed by reflection in this sphere here. And this one on the right, this is an image formed by refraction with this lens here. So over here on the left-hand side, there's an object, a tree, and we're looking at an image of the tree, a likeness, a copy, a representation of the tree. In this one on the right, there is an object, this person's eye, and we're looking at the image of the person's eye, this copy, this likeness, this representation of the eye. Now, a couple of points. This happens to be a convex mirror, and we'll discuss that later. This happens to be a convex lens. We'll discuss that later. But with these two examples, you see some of the changes that you can accomplish, some of the changes you can make when you form images by mirrors or by lenses. So this image over here of the tree, that image is minified. Now, I don't know if minified is a real word, but it means shrunken to me. It's a smaller image of the tree. The tree is really bigger than this. This image over here on the right, this is magnified. That is a real word, I know that. That means that the image is an expanded version of the object. Another couple of features here, that this image here of the tree is upright. It's the right way up. The leaves are at the top and the roots are at the bottom. This image of the eye is the right way up. The eyebrows at the top and there's just a few eyelashes at the bottom. So these are upright images. What we'll discover is you can turn the object upside down in the image and make an inverted image. So that's another thing you can do. These are also both what we call virtual images. For example, over here, the light that we're seeing for this image of the tree, it looks like it's coming from behind the mirror. But obviously it can't physically be coming from behind the mirror. That's a virtual image. And so there's a number of properties of images, whether they're magnified or minified, made bigger or smaller, whether they're upright or inverted, the right way up or the upside down way up, and whether they're what we call real and virtual, that we're going to explore in today's class, and we'll also explore in the next class. Okay, so keys to understanding image formation. What was I trying to tell you here? Well, I better read it out because I've forgotten. Images are formed using mirrors by reflection. Okay, so there's just a reflection of light off the mirror, and that reflection of light off the mirror forms the image of the object by the mirror. Images formed by lenses, they're formed by refraction, the passing of the light through the lens, the glass or the plastic of the lens. And so that's how images with lenses are formed by refraction of the light from the object. Images, as I mentioned, can be made bigger and smaller, magnified, minified. They can be the right way up or the wrong way up, upright or inverted, we say, and they can be what we call real or virtual, meaning that the light actually is coming from where the image looks to be, and where the light is actually not coming from where the image appears to be. So those are two cases. It turns out in this sort of world of images formed by objects, by lenses, and by mirrors, there's a sort of simple, approximate way of figuring out the properties of the image from the nature of the object. That's what we're going to focus on in this class and next class. So simple rules that use diagrams, ray tracing, simple rules that use formulas to figure out the image properties. There are actually, if you went deeper into the problem, you went closer into the problem, it's actually a much more complicated world. And we're not going to touch on that. We're just going to touch on the simple rules for image formation. Okay, the only thing we need, the only prerequisite we need to understand the image images formed by mirrors in today's class. The only thing we need from the last class is the law of reflection from the last class. And the law of reflection, I've just refreshed our understanding of it here. Here's an example of refraction. We've got a medium in which the light is traveling upstairs here above the horizontal line. The horizontal line is representing a boundary between two media. Maybe this is the surface of a mirror, or maybe this is the surface of a still pond or a still lake. And what we're seeing is light reflected off the surface of the mirror, or reflected off the surface of the pond or the lake. And what we're seeing here is the law of reflection, that the incident angle, I called it theta I, and remember we measure it with respect to the normal to the boundary, is equal to the reflected angle, I called it theta R, and again it's measured with respect to the normal to the boundary. So it's just this law of reflection that we're going to use today. This is the law of specular reflection. Okay, so let's start with planar mirrors, flat mirrors, and then we'll move on to curved mirrors, convex, concave mirrors. So here's a diagram of reflection from a plane mirror. This is how we would draw reflection of light from a plane mirror using our law of reflection. And it's going to, this diagram introduces us to some of the language, the terminology that we'll use, some of the tools, the techniques that we'll use in drawing images. So I'll go through all the details on this diagram. So here vertically in light blue, this is the plane mirror. This thing, this vertical arrow that I'm calling the object, is the tree or the person or the whatever that I'm making the image of. So we call it the object. I'm going to give it the symbol O. Over here on the right hand side, we'll discover that this is the image that's formed by the object, the image that you see in the mirror, and we indicate that with this vertical arrow here. So this would represent the image of the tree or the person or the whatever, and we call it the image. I'll denote it I. Those two quantities, the object and the image, I've located them, I position them on this axis here that's perpendicular to the mirror, 90 degrees to the mirror. We call this the optical axis. So we place our object on the optical axis, we're going to see our image on the optical axis. This is how we draw these ray tracing diagrams for plane mirrors, for curved mirrors, for lenses, for all sorts of lenses. Okay, there is a front side to a mirror, obviously we know that, we've been in the bathroom. There's a back side to the mirror, we know that if we've been in the bathroom. Then the light approaches the mirror from the front side. It's going to reflect off that. We're going to see that the image appears behind the mirror. And we'll see that. Okay, so now we've got an understanding of the mirror, the optical axis, and the object and the image. Let me show you how I concluded that the image appears over here on the right when the object was over here on the left in front of the mirror. I drew rays. I traced rays that come from the object that reflect off the mirror and then head into my eye. My eye's over here, my giant eye's here, and this eye is seeing rays that came from the object but were reflected off the mirror. I drew two rays on this sketch, and both of them obey the law of reflection. One of them is in blue, so it's this ray here. So it comes from the object, the tree, the person, the whatever, and it strikes the mirror. It strikes the mirror and it's reflected off the mirror and goes back to my eye. So I'm going to use that in constructing where the image is formed. I drew a second one, this red one here. It also comes off the object, the tree, the person, the whatever, strikes the mirror, obeys the law of reflection, it's reflected off the mirror, and it's going to also go into my eye. I drew these rays. These rays are handy ones to draw. One of them, the blue one, you notice, travels towards the mirror parallel to the optical axis. That means it strikes the planar mirror at incident angle 0 degrees. It means it will be reflected at incident angle 0 degree. Sorry, reflected angle 0 degrees. And so it heads in at 0 degrees to the normal. It returns at 0 degrees to normal. It returns along the path that it headed into the mirror. And so we see it reflected backwards here. That's just obeying the law of reflection. Same thing for the red ray. It heads in. This particular ray is another special ray. It hits the mirror at the location of the optical axis, where the optical axis traverses the mirror. So it heads downwards to that point, that location, and it's reflected off the mirror towards my eye. And again, it's obeying the law of reflection. So the incident angle, which would be in here, is equal to the reflected angle, which is downstairs here. So it obeys the law of reflection. So I've drawn two rays obeying the law of reflection. Two rays that are relatively simple rays to construct, because one is parallel out and one is in towards the optical axis, away from the optical axis. That's why I picked those two. Now here's my eye. Behind my eye is my brain, and my eye is I know nothing about this stuff, but somehow there's some sort of retina back there and it's seeing this light, it's recording that light. My brain, I know nothing about this, but it's sort of interpreting this light. And look, it thinks, oh, there's a ray coming in upstairs here, so it's light coming from this path here. There's a ray coming in on this path downstairs here, so there's something back here. It traces these two rays back, they intercept here, and this is the location of the image. So this is where I think the image is formed, and where the image is formed of these. It's where these rays that came from the same point on the object appear to meet for the image. So that's the image location. And so that's a simple example of ray tracing to form a image from an object. It was a simple one because it's a plane mirror. We can make more complicated ones. It was a relatively simple one. We traced two rays, two very important rays. But we got to learn the language of ray tracing. We got to learn the language of object O, image I, the optical axis, the sort of rays that we will draw in ray tracing. So we got to explore that world. That ray tracing actually leads to a couple of equations that describe the images that are formed by plane mirrors. General equations that will describe the images formed by plane mirrors. These equations they're written downstairs here at the bottom, but let me just say that where they come from. When we constructed these two rays that were reflected off the mirror to construct the image formation, knowing the object position, we actually, geometrically, we constructed two triangles. There's a green one over here, that's on the front side of the mirror, and there's the magenta one over here on the back side of the mirror. So this one on the front side of the mirror, two of the sides of that are the real rays, the blue ray and the red ray, heading in towards the mirror. The two of the sides of the magenta triangle, they're not real rays, they're these dashed lines. That's where the rays appear to come from, behind the mirror. So this top side and this hypotenuse here. But you'll notice in this construction that this green triangle and this magenta triangle, they're identical shaped triangles. That means that the image position is as far behind the mirror as the object position was in front of the mirror. It means that the image height, what I called h prime here, is the same as the object height in front of the mirror. So from this little construction, from this bit of geometry of two identical triangles, we're able to conclude that the position of the image, we call that Q, is an equal distance behind the behind the mirror, that the object is in front of the mirror. We call that object distance p. And that the height of the image, we call it h prime, is equal to the height of the object. And so that's a rule for how the image is formed, where it's located, how big or small it is in terms of where the object is located and how big or small it is. So we've now got a general rule and a pair of equations that really describe the nature of the image in terms of the original object. Let me make a couple of additional remarks about these equations. So look, I put Q, remember that's the image position behind the mirror, is equal to the object position, that's the object position P in front of the mirror, Q is equal to minus P. Why the minus sign? The minus sign is because we call positions in front of the mirror, that's the positive side of the mirror. So a position in front of the mirror is a positive number. The positions behind the mirror, to denote that it's behind the mirror, we give it a negative sign. So a position behind the mirror has a negative sign. So Q equals minus P in this depiction here. Because the object was in front of the mirror, the image is behind the mirror. So they have the opposite signs of their positions. Their distances are the same, but the signs are opposite one another. There's another remark. I did mention that in general, with mirrors and with lenses, you can sometimes get upright images and sometimes get inverted images. They'd be the right way up or the wrong way up. In this case, we got an image that is the same way up, the right way up, as the object. This plus sign here is used to indicate whether the image is the right way up or it's inverted, it's upside down. So if this is a plus sign, then that tells us we got an image that's the right way up. That's how we constructed this image here. If this was a minus sign, the image would be upside down. Normally we actually think about this equation. This is an equation for the magnification. So that's just the ratio of the image height to the object height, h prime over h. And in this particular case, our equation based on these right angle triangles says that ratio, that magnification is +1. So the 1 means it's the same size, and the plus sign here, that just means that it's the same way up as the object. So if I was describing this image that was formed by this object in this plane mirror, I would say that firstly, it's neither magnified nor minified, it's the same size. Magnification is 1. I would say that it's the same distance behind the mirror, that the object is in front of the mirror, so that's where it's located. I would say that it's an upright image because it's the same way up as the object. The magnification is positive, tells me that. And then finally I would say that this is a virtual image. This is a virtual image because it looks like the image is behind the mirror. It looks like the light is coming from behind the mirror. But obviously the light doesn't come from behind the mirror. The wall is behind the mirror. And so this is what we call a virtual image. Where am I going? Going the wrong way. Okay, let me show you a little demonstration of this, of reflection from a planar mirror. I'm going to show you this one as a sort of reference point. It's not so interesting, I think, for a planar mirror to see the reflected light rays off the planar mirror, but it's going to be much more interesting when we look to reflected light of concave convex mirrors, the curved mirrors. So this is, in some sense, a reference point. So on this video, I've got this device here. So this device produces parallel rays of light that will travel from the left, the device, over here towards the right. And so there'll be a parallel ray of light coming out of this this location, one out of this central location, and one out of this lower location. And so these are the rays that I was tracing in my sketch, these parallel rays of light. So we're going to look at those. This device here, what's this? This is just a device in which I can fix a plane mirror or a curved mirror, convex mirror, concave mirror. So it's just a support. So if we just run this, I'm going to put a plane mirror in the support. Here I am at my assistant. And that's a plane mirror, by the way. That's a flat mirrored surface that I've fixed here. And then I'm going to switch on this device. So I'm going to turn the lights off so we can all see it. And then I'm going to switch on the device. Look at these three beautiful plane rays traveling parallel to the optical axis. They're going to strike the mirror. In this case, the light is reflected exactly back along where they came. That's because they're striking the mirror at 0 degrees to the optical axis, so the reflected light is 0 degrees to the optical axis, and so the light came back in the direction they went. Now I'm changing the angle of incidence, so I'm changing the angle of reflection, and you're seeing now the reflected rays. And so when we construct these images of objects forming planar mirrors, it's just this ray tracing that we're using. It's just that ray tracing that we're using. What am I doing? Good question. Okay, let's move on to curved mirrors. And this was an example of a curved mirror. This is an example of a convex curved mirror. There's also concave curved mirrors, and I think I'm going to start with the concave mirrors and then move on to convex mirrors. Okay, so here's a mirror, this curved surface here. The mirrored surface is on this left-hand side, and so over here on the left is in front of the mirror. This is where we would put our object, our tree, our person, or whatever. And over here on the right-hand side, this is behind the mirror. This is where we might see the image as appearing to come from, behind the mirror here. To the sketch of the mirror, I've added a few things. So I've added the optical axis. We're familiar with that now. There's this horizontal line here, and it goes through the center of the mirror. But on the optical axis, I've now added two points, two locations. These 2 points, these 2 locations are very important for curved mirrors. One of them is the radius of curvature of the mirror. That's a geometrical thing that's important. And you might guess where that is. The other one, new thing, is the focal length, the focal point of the mirror. And that's a new thing. You wouldn't just guess where that is. So let me introduce those things. The radius of curvature is this point here labeled C. And it's simply, this circular surface of the mirror is forming a circle, forming an arc of a circle that's centered on this point, right? So this distance here is the radius of curvature. This point we call the radius of curvature. So that's what that point is. This point here, this is halfway between the radius of curvature and the location where the optical axis strikes the center of the mirror. So it's equidistance between this point on the left and this location over here on the right. And that's the point we call the focal length, the focal point. And that's going to be very important for curved mirrors, very important for concave, convex mirrors when we construct our ray tracing. It's also going to be very important we'll see, for lenses, diverging, converging lenses. We'll use that focal point when constructing our ray tracing. So it's a very important point. Let me make a couple of remarks about these 2 points. So this mirror here is a converging mirror. We'll see, it bends the light towards the optical axis. And for a converging mirror, the radius of curvature, what we call R, and this focal length are positive numbers. So in this particular drawing, R and F are positive numbers. You could imagine a mirror curved the other way. So this mirror is kind of forming a cave around C and F. But you could imagine a mirror that's curved the other way. That would be a convex mirror. That type of mirror diverges light rays, bends them away from the optical axis. That would have a negative value for the radius of curvature and the focal length. So just again, the focal length and the radius of curvature kind of describe the personality of the curved mirror. There's 2 like introversion, extroversion, like neurotic, not neurotic. Right? There's 2 kind of poles to curved mirrors. They can be convex, concave. So convex, concave are distinguished by either positive signs for the focal length and radius of curvature or negative signs for the focal length and radius of curvature. And then within a class, within introversion, you can, or within extroversion, right, the equivalent of the positive and negative here, you can be very extrovert or just a bit extrovert. You could be very introvert or just a bit introvert. And the same thing is here. When you have a positive focal length, it could be a small number, meaning it's very close to the mirror. It could be a big number, meaning it's quite far from the mirror. If you have a negative if you have a convex mirror with a negative focal length, again, it could be a small negative focal length or a large negative focal length. So there's a whole spectrum of extrovertism, introvertism for our mirrors. Okay. So this is ray tracing for this convex mirror. At first sight, this might look horrific. This looks really awful. But I'm going to talk our way through this drawing here. This sketch here is how we construct, with ray tracing, the image that's formed by an object in a curved, this case it's a concave mirror. So let's go through all of that. Firstly, let's familiarize ourselves. This is the mirror over here. So this is the front surface on the left. This is the back surface on the right. This is the optical axis, this black line here. This gray vertical arrow here that I labeled O and labeled its position as P, this is the object. So this is the real tree, the real person, or the real whatever. Downstairs here, we'll find out why it's here and why it's this size. But I labeled this arrow as I labeled it as I, its location as Q. This is the image. This is where the image is formed, and this is the properties of the image. So here was the object in gray, here is the image in pink, and I used ray tracing to find out where the image is and what the image looks like, knowing that the object is here and looks like this. There are 4 rays on this picture. To find the image on a curved mirror, you really want to draw several rays. And actually I've drawn the 4 easiest rays to draw just to make clear that we are locating the image, just to be certain that I'm locating the image. So I'm going to go now through, now we've introduced, where the mirror is, where the optical axis is, where the object is, where the image is. I'm going to go through the 4 rays that I drew. So there's black, red, and blue and green. And I call them the physics simplest ray, that's the black one. Red is the kind of geometry simplest ray, and then there's twins. There's brother and sister. There's the blue and gray ray. Oh, I said they were cousins here. So I'll explain that. Okay, let's start with the black ray. This is the physics simplest ray because this one heads from the arrowhead of the object. So all of these are coming from the object because the light's coming from the object and we want to find where the image appears to be when we look in the mirror. This ray comes from the tip of the object, and the physics simplest ray strikes the mirror at the location of the optical axis. It makes an incident angle with the optical axis, so that's the angle of incidence, and the reflected ray will obey the law of reflection, so it makes the same angle with the optical axis but below the axis. And so this black ray heading out here is at the same reflected angle as this black ray heading in here. And that's just the law of reflection. And it's the simplest ray because it's the one where you can most easily see the law of reflection at work. The incident angle equals reflected angle. So this is one ray that you can construct, and I've done it. There's another ray, the simplest geometrical ray. That's the red ray. It also comes from the same location. This ray, the rule for this ray is going to pass through the radius of curvature. So look, that's the key point here. If you head towards the mirror through the radius of curvature, you're going to strike the mirror perpendicular to the face of the mirror because you're traveling along a radius, so like a spoke on a wheel. And the spoke on the wheel, like this radius here, strikes the wheel or strikes the mirror perpendicular to the mirror. So 0 degrees incident angle, so 0 degrees reflected angle, the light will be reflected back through the radius of curvature along the path it came from. So that's a simple ray that you can draw and construct using the radius of curvature. So we've got those two rays now. Blue and green. Cousins, brother and sister, or whatever. Okay, the rules for those is that one of them heads in parallel to the optical axis and then reflects back through the focal point. The other one does the reverse. The other one heads in through the focal point and reflects back parallel to the optical axis. So these two rays are now using this very important point we call the focal point. So let's see how I construct those. The blue one heads in parallel to the optical axis. This blue line is parallel to the optical axis, the black line here. And it strikes the mirror. It's going to obey the law of reflection, but how do we make it obey the law of reflection? The trick is you have the reflected ray pass back through the focal point. So this blue reflected ray goes through the focal point. We're using the focal point in the construction of this particular ray tracing. The red one, the green one does the reverse. This one goes in through the focal point, reflects off the mirror, it's going to obey the law of reflection again, and then it reflects off the mirror and runs parallel to the optical axis as it travels away from the mirror. And so those are kind of partners to one another, in parallel, out through the focal point, or in through the focal point. They both involve using the focal point. That's why it's so important. Anyways, that's how I constructed the 4 rays. I hope that's okay. Those 4 rays, after reflection, right, they were traveling over here towards the right. They're now going back towards the left. I didn't draw it, but there's my giant eye here. There's my giant retina. There's my, I don't know what's in there. I don't know. I know nothing about this at all. Anyway, then there's a brain, and the brain interprets where the light is coming from, and the brain says, well, look, the blue ray was coming in this direction, so it's coming, I'm going to trace it back along here. The black ray was coming in this direction down here, so I'm going to retrace it here. The green ray was coming horizontally here, I'm going to retrace that. The red ray was going up here, I'm going to retrace that. I retrace all these 4 rays, I'm doing this very quickly in a fraction of a second in my brain, and they all seem to come from this point here. And this is where the image is located. This is where the arrowhead This light came from the arrowhead of the object. This is where the arrowhead of the image is, and so I just draw that image here. And so with these rays, I've located this image. This image, if we look at it, has a few properties that are interesting. It's been minified. It's been shrunk. We can see that. The pink arrowhead is smaller than the grey one. It's upside down. We can see that too. And it's also, if you were to look at it, you would see it in front of. It would appear to be in front of the mirror. The light appears to be coming from a location in front of the mirror. So that's a real image. Here's actually a picture of that situation. Here's an object. It's the candle. It's placed in front of a concave mirror. And here we're seeing the image. It's smaller. It's inverted. And it's hard to tell in a photograph, but if in reality you would see it in front of the mirror. And so this is an illustration of this particular case. Okay. You can turn all of that into an equation that is based on geometry. And I'm not going to go through it, but you can turn it into an equation that tells you the location of the image, we called that P, in terms of the location of the object. Sorry, we called the location of the image Q, in terms of the location of the object P, and an equation for the magnification of the image, whether it's smaller or bigger, whether it's the right way up or wrong way up. That's this pair of equations here. So there's the mirror equation upstairs. This is all about the location of the image and the object and the nature of the mirror. And then there's downstairs here, this is the magnification equation. This is about whether the image is bigger or smaller and whether it's the right way up or the wrong way up. So the mirror equation says that the sum of the inverse of the object position and the inverse of the image position is equal to the inverse of the focal length. So this equation involves that key property, that personality of the mirror, the curved mirror, is focal length. And it also, the two other things it involves is the object position, P, and the image position, Q. So for example, typically you might know where you put the object. You might know the focal length of your mirror. You want to know where the image is. Well, this equation will tell you that because the image distance Q is the unknown. And so you could solve it for the image distance Q. This equation tells you the magnification. It tells you actually that the magnification, the relative height of the image compared to the object, h prime over h, is equal to this ratio here. It's negative Q over P. So you just take the ratio of the image position to the object position, and that will tell you the magnification. And you can see that at work in this picture here. Look, the image is closer to the mirror, the object is further away, so P is smaller, sorry, Q is smaller, image position is smaller, object position is greater, and so this is going to be less than 1. And so this is going to be less than 1, and so the image is made smaller, and that's what we see here. Also, both the image and the object are on the front face of the mirror. So they're both real. P and Q in this case are both real numbers. This minus sign then makes the magnification a negative number, which is the signature of something being inverted, turned upside down. Okay, demo. Yeah, let me show you this. Okay, so I'm going to go back to this parallel ray generating device, and I'm going to replace that planar mirror, which wasn't so interesting, with a concave mirror. So I'm looking in the cupboard and I found a concave mirror. The mirrored surface is on the inside of the curvature. So it's like making a little cave. That's what concave means. It converges rays. It bends the rays towards the optical axis, and we're going to see that very clearly here. I'm going to turn the lights out, I think. My assistant is going to turn the lights out. And here we see, look, this ray came in along the optical axis, but these other ones are being bent towards the optical axis. The location, if we turn it back, this location here, this is the focal point. This is the focal point. These are the blue and the green rays that I was constructing that kind of went in or out parallel to the optical axis, and they pass through the focal point. They illuminate the focal point for us. They illuminate the kind of the personality of the mirror. Okay, let's finish. Okay. Got to do the same thing for the other category of mirror. That's the convex mirror. Okay, so the mirrored surface is the outer radius of the mirror. In concave, it was the inner surface of the mirror. In concave, we make a cave with the mirrored surface. In convex, the mirrored surface is the outside of the cave. So this slide here is to show you how to construct the image that's formed by a convex mirror rather than a concave mirror. But it's the same process for the convex mirror as it was for the concave mirror. So I'm going to go through it a bit quicker because I'm panicking about the time. Okay, so here's the mirror. The mirrored surface is this outer radius of the mirror rather than the inner radius. This is the front over here on the left, as usual. This is the back over here on the right, as usual. The light is over here, obviously, on the front face. This is the wall. There's no light actually over here on the back face. This is the optical axis, the horizontal black line here again. This gray vertical arrow standing on the optical axis, that's our object again, so it's the tree or the person or the whatever. In pink here, this is the image that gets formed. I've done the ray tracing to find out where it is. It appears to be behind the mirror. It appears to be minified, it's shrunk. And it's actually closer to the surface of the mirror than the object is from the mirror itself. So that's the location of it. So let's see how I found that. I'm going to use exactly the same rays. I'm going to use a ray, the physics simplest ray that illuminates the law of reflection. I'm going to use the geometrically simplest ray that uses the radius of curvature. And I'm going to use the twins or the cousins or the whatevers that head in or head out parallel to the optical axis and use the focal point. Now, the focal point in our construction here, compared to the focal point in our construction for the concave mirror, is we're going to use it on the other side of the mirror. Remember I said that the focal point, focal length and radius of curvature are positive for the concave mirror. They're negative for the convex mirror, meaning that we're going to place them in front or behind the mirror in our constructions, depending on whether we got a concave or a convex mirror. That's actually the heart of getting one mirror to converge rays, the other mirror to diverge rays. So that's a very important thing. And you'll learn this as you actually draw ray tracing yourself. But you'll notice I'm going to use this point and this point on the back side of the mirror rather than the focal length and radius of curvature on the front side of the mirror for this convex mirror. Let's draw the rays. physics simplest case. This black ray here strikes the optic mirror at the optical axis and is reflected off towards the left. You can see here that the incident angle, which is this angle of this ray above the optical axis, is equal to the reflected angle, which is the ray of this ray below the optical axis. So that makes clear the law of reflection here, and that's one ray you can draw. Another ray you can draw, this geometrically simplest ray, uses the radius of curvature. So it's going to head in from the arrowhead towards the radius of curvature. When it heads in to towards the mirror, towards the radius of curvature, which is behind the mirror, it's going to strike the mirror at 0 degrees incident angle, perpendicular to the face of the mirror. So it's reflected at 0 degrees incident angle, so it travels back along its own path. And that's what we see here. The ray comes in, the red ray comes in, the red ray goes out along the same path. So that's the second ray we can draw. Then we got the twins, the cousins, right? We got the blue ray and the red ray, and the green ray. One of them goes in parallel and then is reflected, and we'll construct that reflection using the focal point. The other one goes in using the focal point. We'll construct that, and then comes out parallel to the optical axis. So blue ray heads in parallel to the optical axis, strikes the mirror. It's going to obey the law of reflection here, but it would be hard to, sort of guess where that means that this ray appears at. The way that we construct it is using the focal point again. This ray heads out from the mirror in a direction as if it came from the focal point. So it heads out along this line. The green ray does the reverse. It's going to go in towards the focal point. Of course, now the focal point is negative number, is behind the mirror. It's going to head in towards the focal point. So it heads in this direction. It would strike that location behind the mirror, but it gets reflected off the mirror, obeying the law of reflection. That would be hard for us to draw, but the rule is you head in towards the focal point, you're going to be reflected parallel to the optical axis. And so that's the green ray here. So those are the 4 rays that we can construct for this convex curved mirror. They're the same classes of rays as we constructed for the concave mirror. However, our focal point radius of curvature was now negative and behind the mirror. In the concave mirror, the radius of curvature and focal point were in front of the mirror. So that's a difference in the drawing of these rays. It has a consequence that you see these rays diverge from the optical axis. In the case of the concave mirror, it tends to converge rays towards the optical axis, and that's the difference between these two personalities of negative and positive focal lengths, of concave or convex. Over here, I didn't draw it, it's my giant eye. There's my giant retina with the rods and cones, and you're sending little signals along those neurons or whatever, and they go into my brain, and I got all these different bits of my brain. They're processing where the stuff's coming from, and I retrace the 4 rays. Where do they all appear to come from? Where does the image appears to be? Well, this black one comes along this line here, green one, this line here, red one, this line here, blue one, this line here. All those lines converge at this point. That's where I draw the image. And so I see that the image is a virtual image. It appears to be behind the mirror. Obviously, the light can't come from there. It is what we call virtual. It's shrunk, it's smaller, and it's closer to the face of the mirror than the object was to the face of the mirror. I get all those features. Look, here's a picture of exactly this situation. The candle here is the object. The candle we see in the surface of the mirror, that's the image. This is a convex mirror, and we see that the image in this convex mirror is smaller, it's upright, and we can't tell it from a photograph, but if we were actually here, we would see it behind the surface of the mirror. So it has all of these features that we see in this sketch here. You'll be pleased to know that there's an equation that you can also use to construct the location of the image the size of the image and answer those questions about, is it upright or inverted? Is it magnified or minified? Is it virtual or real? It's this equation here that we call the mirror equation. It's this equation here that we call the magnification. It's exactly the same equations as the mirror equation and the magnification equation that we met for the other mirror, curved mirror, the concave mirror. So the same equations rule for the concave and convex mirror. When you're using them for the concave and convex mirror, what happens differently is that the focal length in one case is positive, the other case is negative. So that will give rise to different locations of an image, of an object in a concave versus a convex mirror. It'll give rise to different magnifications of the image in a convex or a concave mirror. And it'll give rise to, potentially one's real, one's virtual, one's upright, one's inverted, and so on. So it's the same equations. Let me just show you a demonstration of that. The diverging feature of this type of mirror. So my assistant is going to remove that mirror, and now we've got a convex mirror. So the outer radius of the mirror is now the curved surface, and he's going to mount that for me very carefully. And we're going to look at the rays that are reflected off this mirror. And well, there's one ray that hits the center of the mirror and the light is reflected back along its path. But you see these rays here, this one undergoes the law of reflection. This one downstairs here, we'll see when the light's off, well, sort of, undergoes the law of reflection. These rays appear to come from the focal point behind the mirror. And here my assistant is moving the mirror just to show us. I don't know why he's doing it. Okay. So that's converging. Sorry, diverging convex mirrors. Let me just make a remark here. We've met some sign conventions. If you're in front of the mirror, image or object, that's a positive location. If you're behind, that's a negative location. If the magnification is positive, then that's an upright image. If it's negative, that's an inverted image. So those are sign conventions that we use for mirrors. You'll get on a test, get on test 3, a list of these sign conventions, so you don't have to remember them. There's also, I didn't show them in this, so sign conventions I talked about for the focal length and the radius of curvature. You'll get those on the test. You'll also get them, next class we'll talk about lenses, you'll get sign conventions for equivalent sign conventions for lenses. So it's a lot of conventions about what plus and minus signs mean. Okay, so let's turn to some examples, I think. Before I do that, I just want to show you one thing, one more video. Okay, so in this video, I've got a curved mirror. It's over here. And in the first half of the mirror, this is a concave mirror. So the mirrored surface is on the inside. And I'm going to be the object. And I'm going to be the object. So we're going to be looking at my image in the mirror. I'm going to walk towards the mirror, so I'm going to change the object position, and we're going to look at how the image of me changes as I walk towards the mirror. We're going to do this because I'm going to carry a camera as I walk in, and we'll see my reflection here. And then we're going to do the same thing for the other case, which is the convex case. I'm going to walk I'm going to be the object again. I'm going to walk in and walk away from the mirror. We're going to see the properties of the image. We're going to see a very interesting thing. So there's two classes of mirrors, concave, convex. One of them actually can magnify. One of them can't. And we'll see that. This concave one can magnify. The convex one can't. We'll also see that this concave one can turn things upside down, can invert things. Convex one can't do that. And so this is going to be an illustration of this. This is basically exploring this world of where you put the image, what the object will look like. So let me run this. And actually, you might see me in this, not very clear, this is me. I'm upside down, here's my head, and here's my feet. I will become clearer as I move in closer. I'm wobbling around a bit as if I've been drinking wine before this, but I don't think I was. I really am stumbling around, but you can see me moving in, and I am upside down, so I am inverted, and I'm getting pretty large as I get close, and then suddenly, whoop, I'm the right way up, and I'm magnified. And that's a property of a convex, concave mirror. So I'm magnified, I'm walking backwards now, and then suddenly I'm inverted again, and my image is kind of receding behind the mirror as I recede in front of the mirror. So that's the world of a concave mirror. Now you notice I changed the mirror quickly. This is a convex mirror, so the outer surface is curved. I'm the right way up here. Look, I'm the correct way up. I'm walking towards the mirror. I'm smaller than I actually are. I am being shrunk in the mirror, but I'm staying the right way up, and I stay the right way up all the time. This mirror can't magnify me, and this mirror can't invert me. So this is a convex mirror. And then I walk away. And I'm always minified and always the right way up. You might therefore use a convex, a concave mirror which could magnify. You might use that in a microscope, or you might use it in a telescope if you want to magnify things. That would be a good use of it. That's a good idea I just had, but unfortunately people had that idea hundreds of years ago, so it's no good. Or you could use the concave mirror. They'll use that in, now they usually use cameras, but they would use it in stores, right? So that, the person behind the register can see the whole, what's going on in the whole store, because it minifies and you can see much greater region of the store. Okay, let's look at an illustration example. This is for a plane mirror. I'm going to try and do two examples. Plane mirror and a curved mirror. A choir stands along the right wall. Okay, here's the choir. And an organist sits near the left wall. Here's the organist. The organist uses a mirror to see the choir. And the question is, if the mirror is 0.6 meters wide, then how much of the choir, what width of the choir can the organist see in the mirror? This is a plane mirror. It's about constructing rays with plane mirrors using the law of reflection. Like a lot of optics problems, it involves a bit of geometry in constructing these rays. So we're going to go ahead and do that. Just again, we got the organist over here, 0.8 meters from this left-hand wall, looking at a mirror. We got a wall, in which the choir is lined up here, that's 5.3 meters away from the left-hand wall, and we want to know how much of the choir can the organist see. Okay, so I constructed a sketch of the image of the choir that's seen by the organist in the mirror on the left-hand wall. So I'm doing exactly what I did in those very first few slides with the planar mirror. I'm constructing an image of an object using the laws of reflection, using my rules for a planar mirror. I've drawn here a couple of rays. I'll describe the rays. Again, the object is the choir over at the right-hand wall, gosh, and I'm trying to construct the image of the choir that's seen by the organist in the mirror. This is where the image is going to be located. We'll see. In doing that, you know, I could draw a couple of rays. So one ray I could draw is this ray here that travels from the object and bounces off the mirror. I could draw that ray. That's a familiar ray. Another ray I could imagine drawing is this one here that travels parallel to the optical axis and bounces off back in this direction. So I could construct those rays. I have constructed the image position based on what we discovered was the law of the image location and magnification from our earlier slides. We said that the image is located behind the mirror. If our object here is in front of the mirror, it's equal distance behind the mirror that the object is in front of the mirror, i.e. Q equals minus P. So this distance here of the image from the mirror is the same as this distance here of the object from the mirror. It's just that this image is located behind the mirror. It's going to have a minus sign. This object was located in front of the mirror. It's going to have a positive sign. So that's how I've located this image here. The magnification of a planar flat mirror, we said, is +1. Okay, which means that it's upright. It's the same way up, and it's neither minified or magnified. It's the same size. And so that's how I drew this image here. It's exactly the same size as this object over here. So I've constructed that image based on my laws for a flat planar mirror, that I'm going to get an image that's behind the mirror, same distance behind the mirror that the object is in front of the mirror, and I'm going to get an image that is the same size as the object. The magnification's 1. That's all that went into this drawing here. Based on this drawing, right now, so at this point, this was my first step in the solution. I've just used my understanding of flat planar mirrors to draw the image based on the object and knowing the mirror. Now I'm going to use a little bit of geometry to answer the question. Here's the geometry I'm going to use. Over here on the left-hand side are two similar triangles. Similar triangles are triangles that have the same shape, which means that they have the same angles, but they might have different overall dimensions. One might be bigger, one might be smaller. The ratios of their hypotenuse would be the same as the ratios of their adjacents, the ratios of their objects. That's what similar means. They're the same shapes. There's a little triangle, this green one here, and there's a big triangle, this magenta one here, that are similar triangles. They're the same shape. They have the same angles in all their corners. They just, the hypotenuse, the opposite, the adjacent are all bigger for the magenta triangle, correspondingly bigger. They're all correspondingly smaller for the green triangle. The green triangle, I know the length of the vertical side is half the width of the mirror, and I know the length of the horizontal side. It's the distance of the organist from the mirror. So I know the length of the vertical and horizontal sides for the green triangle. The magenta triangle, I know the horizontal side is 0.8 meters here plus this 5.3 meters here, because we said that's where the object is, but I don't know the vertical side. If I can find the vertical side, I called it y, then I would know how much of the choir I can see. And so I'm just going to use this construction, this geometry based on two similar triangles that's kind of hidden in my construction of the image from the object. Well, the fact that they're similar triangles says that if I take the ratio of the vertical height of the triangle to the horizontal width of the triangle, for the magenta triangle, that's y over 5.3 meters plus 0.8 meters. That's going to be equal to the same ratio for the small green triangle, the vertical height divided by the horizontal width. That's 0.3 meters over 0.8 meters. If you look at this equation here, this ratio of vertical heights and horizontal widths of the triangles, the only quantity I don't know in that ratio is this y here. And so this y here is, we can rearrange for this y here. If you solve for y, you find it's 2.3 meters. And that y is, well, it's 1/2 of the entire width of the wall that you see. It's 1/2 of the entire width of the choir that you see. So if I just multiply that 2.3 meters, I see 4.6 meters or the organist sees 4.6 meters of this right-hand wall. And that's the answer to this question. That's how much of the choir the organist sees in the mirror. So that is an example of using planar mirrors and how the image is formed, that it's neither magnified or magnified, and also how that the image location is the same distance behind the mirror that it is in front of the mirror. Quiz question. What was the magnification? Today's class, we talked about images formed by objects. We talked about images formed by mirrors. We talked about the flat mirror, the convex and concave curved mirrors. We just looked at an example illustration of a problem involving a flat mirror. I didn't get to, there's another problem in my slides about a curved mirror going to the dentist. I think I must not have wanted to go to the dentist, so I didn't get time to do that. You might want to look at that. Actually, online I put a few examples on our Canvas page, illustrations of me working through problems involving curved mirrors, so you might want to look at those. Next class, we're going to look at lenses. We're going to look at converging, diverging lenses and the images formed by converging and diverging lenses. You'll see a lot of similarities to what we did in today's class. You get more practice with ray tracing than we just got with today's class. I'll hang out here for 10 minutes if you've got any questions. The magnification for This quiz, the magnification is 1. Planar mirrors, flat mirrors, always magnify. Always have a magnification of +1. The object, the image is the same size as the object, and it's the right way up.